Up until this point, we've solved lots of differential equations, but they were always of the form that whatever the derivative was with respect to, what was over on the other side was a function of that variable. So we could see that if we just multiplied by dx and integrated on both sides here, that we'd be able to get the answer, because the antiderivative of the derivative with respect to x is just going to be the function, right? And we have the integral of the function dx over here. So for example, if we had dy dx was equal to some function of x, like maybe x squared plus sine x, then we could just integrate in order to find the answer. So let's see, the antiderivative of x squared is 1/3 x cubed, and the antiderivative of sine is negative cosine x plus c. We're able to find the answer. Now, it doesn't quite work if what's over on the other side depends on not only the independent variable, but on the dependent variable y. So in this case, if you try to integrate both sides with respect to x, over here you'll get y, but here you have the integral of f of xy times dx. I can't figure out what that integral is until I know what y is, but I can't figure out what y is until I know what the integral is. So we have kind of a bit of a chicken and the egg problem, right? I need to know what y is. Well, y is that integral. I guess I could try to stuff that in there. Integral of f of xy dx, dx. Except for then I need to know what y is in here. You see, I'm going to get like a descent into madness as I keep plugging in this integral over and over and over again. So I don't know what the piece is, right? As an example, let's consider this problem. If you look at it, we have dy dx, and it's equal to a function of x and y over here on the right-hand side. If we try to do what we've always done, which would just be to integrate both sides with respect to x, then on the left-hand side will actually be okay, because we're talking about the integral of dy dx with respect to x. We're just asking what's the antiderivative of dy dx, which is obviously y. Over here, two of the terms I'm okay with. The antiderivative of x is 1/2 x squared. The antiderivative of negative 2 is negative 2x. But I have a problem with these two. I don't know how to find the antiderivative of negative 3xy, and I don't know how to find the antiderivative of 6y. The issue is, I need to know how does y depend on x? What is y as a function of x before I could find its antiderivative? But that's what I'm trying to do, is to find y. So I'm kind of stuck here. However, if the function on the right could be written as the product of two functions, one of which was a function of x alone and the other was a function of y, then I could separate the problem. I could divide both sides by the function of y, and then I could integrate both sides with respect to x. When you do that, dy dx times dx, that is dy, and then over on this side, this is a g, so g of y. So I have on the left-hand side an integral of a function of y with respect to y. That should be okay as long as the function is not too complicated. And we have the antiderivative of a function of x with respect to x. So the problem basically separated out. We call a function that fits this form, that you can separate in this way, separable. So because the right-hand side is the product of two functions. In this case, we can actually separate this by factoring. And these first two, if I factor by grouping, the first two have a common x, so if I pull it out, I have 1 minus 3y. The second two terms, I could make a matching 1 minus 3y if I pulled out a negative 2. Take out negative 2 and you have 1 here and negative 3y. So, because the 1 minus 3y is common to both terms, I could factor that whole thing out. I'd be left with x minus 2 times 1 minus 3y. See how that fits this pattern? We have a function of x right here times a function of y right here. So to solve this, let's just apply the idea that we saw here. Let's try to separate and then integrate. What I'm going to do is I'm going to divide both sides by that function of y alone, and then I'll integrate both sides with respect to x. Now dy dx times dx, that's just dy. So we have dy over 1 minus 3y. Over here we have the antiderivative of x minus 2 dx. So the antiderivative of the right-hand side is easy, 1/2 x squared minus 2x plus some constant. Over here, the derivative of 1 minus 3y would be negative 3, so I see if I slip a negative 3 in here, which would also require me to divide by negative 3, I don't really need that one, so I'll bring it outside since it's a constant. Now I can see I have the derivative of a function over the function. That's a natural log, so I recognize the antiderivative as being the natural log of the absolute value of 1 minus 3y. There's also an arbitrary constant here, but I could move it over to be with this arbitrary constant and just combine them into a single arbitrary constant. Okay, so now I've got the integration part done, right? All I could do would be to solve for y. I'm going to multiply through by negative 3, so I get natural log of 1 minus 3y equals negative 3/2 x squared. Negative 3 times 2x, negative 2x would be plus 6x. Negative 3 times an arbitrary constant is yet another arbitrary constant, which I'll sort of sloppily continue to call c, since negative 6 times a number that's arbitrary could be anything else, so I'll just rename that. Okay, now to get rid of these, I have the absolute value of 1 minus 3y is e to all that, negative 3/2 x squared plus 6x plus c. And I could think about this as being e to the negative 3/2 x squared plus 6x times e to some arbitrary constant. But e to an arbitrary constant could make any positive number, so this is again another arbitrary positive constant. The absolute value of 1 minus 3y is that, so 1 minus 3y must be either plus or minus this arbitrary constant e to the c. Well, so e to the c had to be positive, so now it could be anything again. So 1 minus 3y equals c. E to the negative 3/2 x squared plus 6. Here, this plus or minus e to the c, I'm just writing that as some other arbitrary constant. Finally, to solve for y, you need to subtract 1 from both sides and divide both sides by negative 3. So we have y is equal to negative 1/3 times an arbitrary constant, huh? Okay, negative 1/3 an arbitrary constant times e to the negative 3/2 x squared plus 6, and negative 1 divided by negative 3 would be plus 1/3 there. You could argue that negative 1/3 times an arbitrary constant is yet another arbitrary constant, but the point is, by separating, I was able to integrate, and once I had integrated, then it's possible to get y alone, so you can get a solution to this differential equation. You go from having information about how y changes to having actual information about the function y.